Alright, this is how to draw a free body diagram. So, let's say we have an elevator, right? And our elevator has to be represented as a singular dot. It can't be represented as a rectangle, a square, or any other shape. It always has to be represented as a dot. That's like the most important part too. And the elevator which is the dot right here, it's moving downward at a constant velocity. That means the acceleration would be zero because it's not speeding up or slowing down. So it's constant. So we would draw gravity first of all because that's a key factor. So this would be you would basically label this as force G, which means the force of gravity. And as we said before, it's moving down at a constant velocity, which means it's not slowing down or speeding up by any means. And by Newton's second law, if acceleration is zero, then the net force is zero. That means the upward tension of the force of the cable is exactly like the same as this. It's the same exact magnitude to the downward gravitational force, which is weight. So you would also have it in equal size, equal length, the vector. And you would label this, since elevators are connected to a rope or a string, you could say, this would be force T, which is tension. So this is basically the free body diagram of elevator that's going down at a constant velocity. And it's constant because Newton's second law, which says, or in this term, if the acceleration is zero, then the net force is zero. And yeah, that's the example one. But if we were to say, hold on now, if we were to say that the elevator is going down faster than usual, accelerating basically, then acceleration is downward. That means like the net force must be downward. And we know this because gravity always pulls downward, and the thing that opposes it, because there's always going to be a tension that, or like not a tension, a force that opposes something, it pulls upward, which is in this case the tension. So I need to make that a little smaller. So here we have the tension for force. So you'd label this as Ft for tension. And at the bottom, since the elevator is accelerating downwards, the gravity vector would be bigger than the vector that's opposing it, the force that's opposing it. So this would be Fg for gravity, force of gravity. So, and if it were to accelerate going upwards, it would be reversed. The tension would be higher than the gravity, and so on. So that's basically how you draw a free body diagram for an elevator. If it's stable, if it's going faster than normal, going up and down faster, acceleration, all that, always. It's gonna always look something like this if it's going downwards, vice versa if it's going upwards, and both vectors would be the same length if it's going constant up or down.